Hello there, welcome back to another video. Today we're going to be stepping away from derivatives for a little bit and we're going to be talking about limits. Now limits are just techniques that help you figure out how a function behaves as it approaches a certain point. Now we talked about this in the what is a derivative video, but today we're going to be doing a little bit of a deeper dive into specifically limits. And I'm going to be talking to you about the multiple different types of limits and how we can solve them. And before we do that, I want to talk about the different steps and the notation of limits. So before we begin, what is limit notation? Limit notation looks exactly like this. We say it as limit as x approaches n of f of x. So that's what we're looking for here. And x approaches n is just a certain point. So this is the point we're going to try and plug in and find the behavior of the function at. So far so good. Now the different steps we want to look at for limits. The first step of limits is plugging in the actual value that it's trying to approach. This is very easy if we find some sort of defined limit. What that basically means is the place where I'm trying to find my limit. So for example, if I have this function here, and let's say my limit is somewhere here. Well, that's a defined value on my function, right? So I don't need to try and find its behavior because I already know it's defined at that value. Which means all I got to do is say, okay, for example, if f of 3 is 4, and my limit as x approaches 3 of f of x, if I want to try and find that, will be 4. So all I got to do is just plug in the y value that gives me this x value. That's only if it's defined though. Now for step 2, it's a little bit more tricky. We need to see whether it's one of two things, 0 over 0 or any number b over 0. So this is called asymptote. This is the asymptotic behavior. And this is indeterminate. Now asymptotic is associated with any sort of reciprocal function or any sort of function with a horizontal asymptote. So asymptote basically means that a function approaches a certain number as it approaches infinity, right? So if I have a vertical asymptote, as my function approaches the x value of 0, for example here, it approaches infinity. So that is an asymptote, and we can get into ways of solving and getting around that as well. Then we have the indeterminate form. Indeterminate basically means that my x values will cancel out in a way and it will give me 0 over 0. And this is actually the most interesting form. This is where most of our limits and skills will come into the indeterminate form. Because over here we can use things like L'Hopital's rule, we can use factoring, and we can use rationalization. So this is sort of our process here. Step 1, if plugin doesn't work, if we can't plug in the value, then it's going to give us step 2. And either it's going to be 0 over 0 or it's going to be b over 0. B over 0 is going to be an asymptote and we can't really do much about that. But if it's 0 over 0, it's an indeterminate form, and that means we can actually mess with it a little bit more. So today we're just going to be doing some examples for these limits. So let's get into it. Okay, first example we're going to be starting off with is quite simple. Limit as x approaches 0 of x squared plus 3. Now, x squared plus 3 doesn't have any restrictions. No matter what number you plug into x squared plus 3, you'll always get some sort of real input. So we actually don't need to worry about this. So we go 0 squared plus 3, and we apply our first step, which is plugging in the x value into the function. So 0 squared plus 3 is equal to 3, and that right there is our answer. This one was a definite limit, defined limit, so it's pretty easy to just plug in the function. Now let's see this one. Limit as x approaches 1 of x over x minus 1. So if we plug in 1 here, we get 1 over 1 minus 1, which is equal to 1 over 0. That right there is a vertical asymptote, right? So if it's a vertical asymptote, we say that it approaches infinity. There's not much else we can do here as we can't really change the asymptote. So over here, your answer will just be infinity because you can't really change an asymptote. You can't really make an asymptote defined, okay? And the behavior, since it's a limit, we can talk about its behavior, and it approaches infinity. Okay, next question. Limit as x approaches infinity. So this one was x approaches 1, but this one is x approaches infinity. So this is talking about the horizontal asymptote, right? Over here, when we look at our graph, what happens if our function goes all the way to the right? So that's what's happening here. And let's see what the function is asking us. X over x minus 1. Okay, now it's very difficult to understand the concept of infinity But I will show you a trick for any sort of horizontal asymptote question so that it's easy to understand. What you want to do is, like the other questions, we want to plug in our x value into the function. So we get infinity divided by infinity minus 1. But the thing is, infinity is so big that subtracting 1 from infinity will still leave it as infinity, right? Because there's no amount of numbers that can add up to infinity. Infinity is just a concept, it's a maximum. So what we can sort of do is we can disregard this 1. So as we can see, now it sort of approaches infinity divided by infinity, right? We can ignore any constants, which means over here it approaches 1. Right, because infinity, any number divided by itself will be 1. So over here, our answer would be 1. So just be careful of that. Whenever we get any sort of limit as x approaches infinity, you want to plug in infinity and check the end behavior. So we ignore any constants. Okay, next question. Another horizontal asymptote question. Here we go. This time let's plug in infinity again. So we get infinity squared divided by infinity minus 1. And that's the same as infinity squared divided by infinity, because we can get rid of this 1, we don't need to worry about that. And infinity squared is significantly bigger than infinity, right? There's a multiplication sort of aspect going on here. So what we can do is we can sort of say that this approaches infinity, because the numerator grows at a much faster rate than the denominator. So there is no limit. Okay, now there's a final situation here with horizontal asymptotes where the numerator is smaller than the denominator. So let's plug in infinity, and we get infinity divided by infinity squared minus 1. Again, we can disregard the minus 1, and that leaves us with infinity divided by infinity squared. If we simplify that, we get 1 over infinity. And we know that 1 over infinity is just 0, right? Because if we divide something by something that's infinitely big, we get 0. So our answer for this one is 0. So as you can see, if the numerator is bigger than the denominator, or in this case, our limit will be infinity. But if our numerator is at the same degree as the denominator, so we have x to the power of 1 or we have x to the power of 1, then we take whatever the coefficient is and we divide them together to get the limit. So over here it's 1 over 1. In the final question here, we get x divided by x squared. So over here the degree of the denominator is bigger, which means we will always get 0. Okay, let's go back to another green question. This is definite integrals. So let's see. If we plug in 3, we get 3 minus 3 whole squared divided by 5. So we get 0 over 5. And be careful, because 0 over 5 is 0, and that's defined. So this isn't like an indeterminate form. It's not like, and it's not an asymptote. So this is actually a defined value. So over here, this will be the correct answer. Okay. Now these are the hardest questions. These are indeterminate questions. So let's have a look here. Okay. With this one, limit as x approaches 2 of x squared minus 3x plus 2 divided by x minus 2. Okay, well straight away we notice that if I plug in x here, it'll give me something, any number divided by 0. And that's not good. We can't have that, right? So what we're going to have to do here is we're going to have to factor this out. Whenever we get a quadratic in a limit question, 9 out of 10 chances say that you should factor it out. So let's factor this quadratic. Let's make it a factor. So we get x squared minus 3x plus 2. We get some product. The product will be 2. Sum will be negative 3. So our roots will be negative 2 comma negative 1, which means we'll get x minus 2, x minus 1. Okay, great. So now we can rewrite this entire thing as x minus 2, x minus 1 divided by x minus 2. And what we can simply do now, right, this is not defying any laws. All we can do is just cancel out what's the same between the denominator and the numerator. So what we've basically done here is we've gotten rid of this pesky little denominator that's been giving us an issue with our limit. So once we've gotten rid of it, all we're left with is x minus 1. And the limit as x approaches 2 of x minus 1 is just a definite integral, right? So that's just 2 minus 1, which is just 1. So that's our final answer for this one. Just be careful, because there are many ways to mess this up, but I think it's very simple. if you figure out what the pattern is. Whenever you have some sort of limit and it's not valid in the denominator and you have a quadratic numerator, always remember to factor out. Okay, on to the next question. Limit as x approaches 0 of sine x over x. So again, if we plug in 0 here, we get sine 0 divided by 0, which is 0 over 0. So that's indeterminate. And another way of solving indeterminate, and this is one of my favorite rules of all time, this is called L'Hopital's rule. And it makes limits very easy, especially the indeterminate ones. What L'Hopital's rule says is that you can take the derivative of the numerator and you can take the derivative of the denominator, and then you can take the limit of those values. So let's try that. Let's take the derivative of sine x. Derivative of sine x is cosine x. Derivative of x is 1. And then we take the limit. So let's make that limit as x approaches 0 of cosine x divided by 1. If we simplify this, we get cosine 0 over 1, which is 1 over 1. And this is a defined value, so that means it is 1. Okay. So remember L'Hopital's rule, because it's quite useful. And, okay, last question here. Limit as x approaches 9 of x minus 9 divided by root x minus 3. So let's plug in 9. So we get 9 minus 9 divided by root 9 minus 3. So we get 0 over 3 minus 3, which is 0 over 0. So that's another indeterminate form. But this time, we can use L'Hopital's rule. It's not illegal to use L'Hopital's rule here. But since we have the square root here, it's a little bit more tricky. So what you can actually do, because there's an easier way here. If you notice, you have x minus 9 and you have root x minus 3. So this is actually a difference of squares, right? So what you can actually do is you can rationalize the denominator. So if something's not working in the denominator and you really don't want it to work and you think it's going to fit better with the numerator, you can multiply. So what you get is limit as x approaches 9 of x minus 9 divided by root x minus 3. And we multiply this by root x plus 3 over root x plus 3. So we haven't added anything to the function. We've just multiplied it by 1 basically. But now we're going to change its forms. So we get limit as x approaches 9 of x minus 9 times root x plus 3 divided by x minus 9. So what we've just done here is we multiplied this root x minus 3 by its conjugate. Its conjugate is basically, we flip this sign here. We flip the cento sign. So instead of having a minus, we put a plus. And that changes everything. So now instead of getting a root in my denominator, I get a normal whole number. And that's x minus 9. And as you can see, now it's become quite easy to simplify. I can just cancel out this and cancel out this. Which means I get my limit as x approaches 9 of root x plus 3. Which means this is a definite limit, which means now I can just plug in root 9 plus 3, and I get 3 plus 3, which is equal to 6. And that is our final answer. So this is it for this video. I hope these questions have made it a little bit easier to understand, and I hope the visualizations have made the thought process behind limits a little bit easier to understand. And remember, there's 3 different types of limits which you should know, and indeterminate is probably the one that you should work with, you should get as comfortable with as possible. So yeah, that's it for this video, and I'll see you in the next one. Bye-bye.